Alright class, today we're going to look at chapter 4.1, the transformations of graphs and symmetry. So, first thing we're going to look at is the shift of functions. So the first thing we need to do is we need to graph this function f of x equals the absolute value of x. Okay, so I'm just going to do a quick hand sketch over here of this graph. You got your y-axis, your x-axis. Now the absolute value of x, I'm going by ones here. Just do a very simple graph from -3 to +3 and on up. So if I plug 0 in, I should get a 0, 0. So that'll be one of my points. Let me change colors. So 0, 0 is a point on the absolute value. 1, 1 is, because the absolute value of 1 is 1. 2, 2 is. 3, 3 is. So this side of the graph looks like this. Alright, now if I plug -3 into the absolute value, I wind up getting, if I plug -1 in the absolute value, I get a +1. If I plug -2 into an absolute value, I get a +2. If I plug -3 into an absolute value, I get a +3. So your absolute value function essentially just looks like a V. Okay, now if we're going to do a shift of this function, and we're going to move this function over to the absolute value of x plus 3, then what that looks like, if I plug in -3 into this function, what I wind up with is -3 absolute value, which gives me a +3. +3 plus 3 is going to wind up being 6. Okay, so at -3, I'm going to have a value of 6. So it'll look like the first point is going to be here. Now if I plug a -2 in, the absolute value of -2 is 2, plus 3 is 5. If I plug a 3 or a -1 in, -1 absolute value is 1, and then we're going to have a 4. So I'm going to get one there. Okay, if I plug 0 in, 0 plus 3 is just 3. It's about right there. And I know it's not perfect. Try to get this point right here to look a little better. Now if I plug 1 in, the absolute value of 1 is 1, plus 3 is 4. Same thing here, the absolute value of 2 plus 3 is 5. The absolute value of 3 plus 3 is 6. So that my new graph here looks very, very similar. The only difference is it shifted up 3 units. 1, 2, 3. Okay, so notice g of x is shifted vertically 3 units from f of x. So this is our g of x function here, our blue. Our f of x function is the red. Okay, so instead of having to take it and graph it piece by piece, we can learn what each of these things do. Okay, so if I've got a number to the outside of my function, it causes it to shift up or down. Okay, so essentially that's what this vertical shifts of graph says. It says if k is a positive real number, the graph of g of x equals f of x plus k can be obtained by shifting the graph of f of x upward k units. So if you take your f of x function, like here, which is the absolute value of x, and you add something to the end of it, you're going to want to shift one up, shifting up. If you subtract something from it, it says the graph of g of x equals f of x minus k can be obtained by shifting the graph of f of x downwards k units. So whatever's on this outside here, we wind up shifting up or down. Okay, if it's positive, we shift up. If it's negative, we shift down. That's what you should learn from that. Now this next part says graph f of x equals the absolute value of x, and g of x equals x minus 5 absolute value. Okay, so if I come over here, we already know what the f of x function looks like here, and that's a terrible, 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 terrible vertical line. I'll try to make it a little better. That's a little better. Okay. So that if I go 1, 2, 3, 1, 2, 3. Our regular f of x function, if we do that again, I believe we did it in red last time. So our regular f of x function for the absolute value of x looks something like this. Oof. Still working on getting used to this computerized drawing thing, so I apologize. Okay. So that's our regular absolute value function, our f of x function. Okay. Now if we graph our g of x function here, and I'll do that in blue, our g of x function is x minus 5. So if I start with -3 again, -3 minus 5 is -8. Okay. So -8 absolute value is +8. Okay. So that what happens is, if I'm at -3, I need to go up +8. Okay. If I'm at -7 or -2, I should be at -7 absolute value, which will be a +7. Okay. If I'm at -1, it's going to be a 6. So let's see, make sure I got this lined up right. I think the 6 needs to go a little higher. I know my graph's not perfect. Okay. 0 is going to be here. 1 is going to be, let's see, absolute value of 1 minus 5, so this -4 should need to be +4. 2 is going to wind up being, let's see, absolute value, 2 minus 5 is -3, so it'll be +3, +2, +1. And here at 5, we actually wind up being 0. Now when I go to 6, 6 minus 5 is 1. 7 minus 5 is 2. And what you see here is, as best I can do it, it continues on that way. So if you look at it here, with this -5 on the inside, we actually wind up moving 5 units to the right. That's what I wanted you to see. Okay, so our original here is f of x, our blue here is g of x, and it's got this -5 in it. So it's on the inside of the absolute value, so it moves it to the right. Okay, so the way this works, like we said, outside moves up and down, inside moves left to right. If you have a negative on the inside, it moves it right. If you have a positive on the inside, it moves it left. So horizontal shifts of graph. If h is a positive real number, the graph of g of x equals f of x minus h can be obtained by moving or shifting the graph of f of x to the right h units. The graph of g of x equals f of x plus h can be obtained by shifting the graph left h units. So notice if you have a positive shifts it left, a negative shifts it right. Okay. So if we've got these here, it says graph f of x equals the square root of x and g of x equals the square root of x plus 3 minus 4. Okay, so instead of trying to hand draw this at this point, I'm actually going to go over to the TI-84 and we're going to draw it and get a really nice drawing of it so that you can see what it looks like on the calculator and see that hopefully with your intuition with the calculator you can kind of see what it does here. Now we can already say before we go to the calculator, okay, on the outside here I've got a -4. -4 means it goes down 4. Now on the inside here I have a +3. Now positive on the inside means it goes left 3. Now let's see if that's right when we look at the calculator. Alright, so we're over here at TI. In my y1 I've got the square root of x. My y2 I've got the square root of x. And then you have to get out of the square root of x and do the -4. Now I'm going to do a standard zoom. So my first function looks like this, my second function looks like this. So if we notice, what happens is we move down 1, 2, 3, 4, and we move left 3, which is exactly what we said that we were going to do by just looking at the function. So down 1, 2, 3, 4, left 3. Okay, so original function, new function. Easy enough. Alright, so the next question says p of x equals negative x minus 55 squared plus 4,500. How many units is the graph f of x minus equals negative x squared shifted vertically and horizontally? Okay. Now, inside is left and right, outside is up and down, right? So it's shifted vertically up 4,500 units, and it's shifted horizontally. Now, is it left or right? We've got a negative on the inside, which means it actually goes right. So this one's shifted vertically up 4,500 units and shifted horizontally right 5,500 units. And if you didn't believe it, wanted to check just to see, you could of course graph it on your TI. Now this one you'd have to kind of work on the zoom a little bit, and you wouldn't probably be able to count it 1, 2, 3, 4, but you could at least see the general directions and make sure you're correct with the right, left, up, down portion. Alright, moving on to page 2. It says the projected percent of U.S. adults populations with diabetes for 2010 through 2050 can be modeled by the power function, and it gives you the power function 4.947x raised to the 0.495 with x equal to the number of years after 2000. Find the power function that models this projection with x equal to the number of years after 2010. Okay, so initially we were at year 2000. Okay, so we're looking at the number of years after 2000. Okay, now we're looking at the number of years after 2010. Okay, we got to figure out, okay, how does that affect it? Now we're looking at our x-axis here, right? X equal to. So if I just draw a little sketch here, this is our y-axis, of course. This is our x-axis. All right. So if our 0 essentially starts at 2000, okay, so we've adjusted it so that our new 0 here is 2000. But now we want to adjust it so that our new 0 is 2010, right? So essentially what we're going to want to do is shift our new 0 right to 2010, okay? So this needs to be here, okay? And I'm hoping you're following me with this. So the 2000 needs to be shifted over and everything so that the whole function, whatever it looks like, so with this power function, whatever it winds up looking like, and I'm not sure off the top of my head, so if it starts here and it looks however it looks, we want to shift it over to where it'll look like that, okay, if that makes sense. So that when we're looking at our graph, our new 0 will technically be that 2010. Okay, so we need to take everything and actually shift it left. Okay, if we're going to shift it left, the inside needs to be positive. Okay, but then you got to ask, okay, where's the inside at? The inside is where this x is. So if I change the color of my marker here, so our new f of x, it needs to shift left 10 units. If it's going to shift left 10 units, it needs to be a positive on the inside. So we need to look at the f of x plus 10. Okay, because that's going to shift it left. Let me make this 10 just look a little bit better. Okay, and I don't think that helped any, but that is a 10. I think it's just getting worse, guys. It's just getting worse. Let's completely start it over. Come on, eraser. Alright, there it is. 1, 0. So that what it looks like is 4.947 x in the parentheses plus 10 raised to the 0.495. Okay, so that would be our new function. That would be our new f of x. So that would be our new power function. This would be it right here. That's our new function. That would be our answer. Easy enough. Sometimes it helps to sketch out a picture, kind of think through the process, and that's the kind of thought process I want you to have. Alright, let's look next at stretching and compressing graphs. So we want to compare the graphs of y equals k to the x squared for k equals 1, 2, and a half. Okay, the easiest way I know to do this, where I'm not sketching it out and looking all crazy, is to go over to the calculator and show you an example of all of them. I feel like you can get a better grasp on the image that way. So let's do that really quick. So if I'm looking at my graphs here, I've got 1x squared, 2x squared, and a half x squared, and I want to see how those compare. I'm going to do a standard zoom. Okay, there's my first one. So my first one's blue, my second one's red, my third one is black. So what I'm looking at here, my first one, just my regular x squared function, is blue. Now 2x squared is my red one, so it actually winds up getting skinnier, right? And it's going to be what we call vertically stretched. Now, this black one is the 1/2 x squared. It actually looks fatter or more spread out. We're going to call it horizontally compressed. And the best way I can explain this is, imagine you hold the very bottom of your graph. For a stretch, you're holding the bottom, pulling the top, is stretching it, it's making it skinnier. For a compress, you're holding the bottom and you're pushing down on the top and you're compressing it, which kind of like if you do it to a ball, makes it expand on the sides. Hopefully that description works for you. Now let's go back to the page. Alright, so our rules here, it says the graph of y equals a times f of x is obtained by vertically stretching the graph of f of x using a factor of, and that's supposed to be an absolute value sign here, a factor of the absolute value of a if the absolute value of a is greater than 1, and vertically compressing the graph of f of x using a factor of the absolute value of a if 0 is less than the absolute value of a is less than 1. And that's essentially what we saw in the graph. So for the half, we compressed, and for the 2, we wound up stretching. So, and the 1 was just the same. So 2 is a stretch, a half is a compress. Alright, next thing we're going to look at is the reflections of graphs. Now this one's pretty simple, so I'm not going to go to the calculator for this one. If you want to graph it on your calculator, get a perfect view of it, be my guest. I'm going to sketch this one out. Okay. So for the first one, I'll do it in blue. Okay. Y equals x squared. So 0, 0 is definitely a point there. Let me draw some tick marks here so we can graph it a little easier. Alright. So that one's blue. Okay, so 1 squared is 1. 2 squared is 4. And that's good enough. But look at negative 1 squared is 1. 2 squared is 4. So if we're looking at a regular y equals x squared graph, it's just your parabola facing up. Okay, so this is y equals x squared. Now if we look at y equals negative x squared, I'll do that one in, say, green. 0, 0 is still a point. Okay. if I plug 1 in here, 1 squared is 1 times a negative is a negative right here. This might not be the best contrast color. Let's make it orange. Okay, if we plug in 2, 2 squared is 4, and a negative out front will be negative 4. Same thing here, negative 1 squared is 1, with a negative out in front of it is a negative 1. Negative 2 squared is 4, with a negative out front is a negative 4. Okay, so that what this winds up being is a parabola facing down. Okay, best I could get it at least. Alright, so what you can see is essentially what this negative does out front is it causes the graph to reflect over the x-axis here. Okay, so these are just reflections over the x-axis. Okay, easy enough, right? So those are easy enough to graph. And if you want to be specific here, you can say y equals negative x squared. But essentially what you need to know is that negative, all it does is it out front, it flips the graph over the x-axis. Okay, now let's look at the next one. It says graph y equals x to the third and y equals negative x to the third with the negative on the inside. Okay, so we'll pull up another graph here. This one's pretty easy to sketch as well. One, two, three. Okay, so if I plug 0 into the first one, so I'll do the first one in blue again. 0 times 0 to the third, or 0 times 0 times 0 is 0, so our first initial point is going to be a 0. Now 1 to the third is just 1. 2 to the third though, 2 times 2 is 4 times 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's actually pretty high up here. Okay, negative 2, negative 1 to the third is actually going to be a negative 1. Negative 2 to the third is going to wind up being a negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. So just to kind of get an initial sketch here, it's going to look, it's a cubic function obviously, so it's going to look something like this. Okay, that's your y equals x to the third. Now if I did the other one, do it in red, y equals negative x to the third. So if I plug in 0, I'm still going to get a 0. So this got this point in common. Alright, if I plug in a 1, negative 1 to the third is negative 1. So what I get is this. If I plug in a 2, then it's going to be negative 2 to the third is negative 8. So that what I get is this. And you'll kind of see that what happens here is that it winds up being reflected in a way. But this time, instead of reflecting over the x-axis, we're actually reflecting over the y-axis here. So if I reflect this over the y-axis, it comes here. If I reflect this over the y-axis, it comes here. Okay. The cool thing about this one, you'd say it was the cool thing, is this actually reflected over the x-axis as well. So if I reflect this over the x-axis, it becomes this. Reflect this over the x-axis, it becomes this. So this is actually reflected in a few ways. But this is definitely reflected over the y and x. So okay. Alright, so reflections of graphs across the coordinate axes. This is the technical definition here. It says the graph of y equals negative f of x can be obtained by reflecting the graph of y equals f of x across the x-axis. So if you put a negative out front of this f of x function, you wind up reflecting it across the x-axis. Okay. Now the graph of y equals negative x can be obtained by reflecting the graph of y equals f of x across the y-axis. So if the negative's on the inside of the f of x function, it winds up reflecting across the y-axis. And it can actually wind up reflecting across both in the more simple style functions. Okay. Alright, so it says graph v equals 2 times 0.01 minus r squared, v equals r squared, and v equals negative 2 times r squared in the viewing window, and it gives you the viewing window here to type into your TI. Okay. Now, you should be able to do that on your own, but I'll go over here and I'll do it for you real quick, and then we'll get over here to the questions. Alright, so I got each of the functions in here. I decided to put them in a different order than the question asked. I decided to do the r squared, which I have represented by x squared here. Then to do the negative 2 r squared and the 2 times 0.01 minus r squared, or x squared here that I'm having to represent it by. Now it gives you the viewing window to do it by. To do that, you go to window, and it asks us to do the window negative 0.1 by 0.1. And you could leave the scale alone, it'll adjust accordingly. Your y here is negative 0.5, or negative 0.05 to positive 0.05. If I graph it now, you can see that this is what it looks like. The very first one is your blue function, the next one is your red function, and then the last one and the final graph that we're interested in is our black function. Okay, so if we start from here, you can see that the initial transformation, we have to flip it. And then after we flip it, we're going to vertically shift it up. Okay, so when you kind of break it down piece by piece, this is what it looks like. So very first piece, just your regular x squared function or your r squared function. We flip it by having that negative out front, and then we are going to move it up. Okay, so let's go over here and kind of figure that part out on paper. Now something you should also notice is that we started with your regular r squared function and then we multiplied it by 2. And something that might not be that obvious on this graph is that even though we've started it by 2, and this one doesn't have the 2 on it, this one's got the 2 on it right there, what's actually happening is you're going to have a vertical stretch of a proportion of 2, so essentially a double, and that might not be as easy to see on the graph as you think it would be. So there's actually a vertical stretch by a factor of 2 between here and here, and it's really kind of hard to see and compare. But what you can see, if you look at the closeness to the x-axis right here, especially where it ends, this blue is a lot closer to the x-axis at the end than this y is. This red is. So this red one is away from the x-axis actually by a factor of 2. And you can probably see that hopefully on yours as well. So your very first x squared function here, this is your negative 2x squared function here, is twice as far away from this x-axis. Okay. Alright, so let's go to the paper and put it all down. Alright, so if we go to put it on paper over here, it says how do I get from v equals r squared to v equals 2 times 0.01 minus r squared. The reason I rephrase it right here and say how do I get from this to this, all I wound up doing was distributing this 2 here, is because to me it's easier to go with this format to words than it is from here to words. Okay, so it is blank about the what axis, so it's going to wind up being reflected about the x-axis here, because remember it flipped over the x-axis. Each r squared value is doubled, and then a shift which direction 0.2 units. And here's where to me it's helpful to have it laid out like this, okay, because even though this 0.01 is on the inside of the parentheses, okay, we're not shifting by 0.01, we're actually shifting by 0.02 and it's not actually contained within where this r is at in the original equations. It's actually on the outside of it, and it's positive, therefore we shift up. So we're going to shift up 0.02 units. Okay, and that's how that works. So sometimes it might help you to simplify it a little bit if possible. So we simplified it from here to here. Alright, let's look at symmetry with respect to the y-axis. The graph of y equals f of x is symmetric with respect to the y-axis if for every point xy on the graph, the point negative x, y is also on the graph. That is, f of x is equal to f of negative x, or f of negative x is equal to f of x, just like I say right here. For all x in the domain of f. Such a function is called an even function, which is important. An example of this is called y equals x squared. Okay, the reason being is, okay, your regular f of x here is x squared. If I plug in a negative x here, what I get is negative x squared, right? Okay, that negative x is essentially the same thing as a negative 1. Okay, and let's not take the x out there, or the squared out that quick. Okay, so it looks like that. Now I can distribute that that squared to everything within the parentheses. So negative 1 squared times x squared. Now negative 1 squared is just positive 1, which is the same thing as that, which is the same thing as that. So essentially f of negative x here is the same thing as f of x here. That's how that works. Now let's look at symmetry with respect to the origin. The graph of y equals f of x is symmetric with respect to the origin if every point xy on the graph, the point negative x negative y is also on the graph. That is, f of negative x equals negative f of x for all x in the domain of f. Such a function is called an odd function. Okay, so an example of this is y equals x to the negative, or x to the third. Okay, we're getting a little tongue tied here. Alright, so if you take it, essentially what it means is if I plug a negative on this inside, it's going to give me a negative on the outside. The way that works, if you want to use your example here to look at it, it's the same thing as f of x equals x to the third. So if I come over here, plug a negative x in, what I get is negative x to the third. Now that negative is the same thing as a negative 1. Okay, I can distribute that third, raised to the third. Oops. Now, negative 1 to the third is the same thing as negative 1, which is the same thing as negative x to the third. Okay, so that you see that what we get is f of negative x is the same thing as negative f of x. Alright. Alright, the other thing we need to look at, symmetry with respect to the x-axis. The graph of the equation is symmetric with respect to the x-axis if for every point xy on the graph, the point x negative y is also on the graph. Note, this wouldn't be a function. It would not pass the vertical line test. Okay. So if we look at this example, we've got y squared equals 9 minus x squared, which is the same thing as plus or minus the square root of 9 minus x squared. Okay, so that essentially, if you graph this, what you get is either an ellipse or a circle. Okay, so if you want to graph this on your function, on your calculator, what you'd have to do, you have to graph y1 equal to the square root of 9 minus x squared, and then y2 equal to negative square root 9 minus x squared. Okay, so those would be the two functions you would graph. Easy enough. And you'll see that obviously that's reflective with respect to the y and the x-axis. Alright, so we've got a whole host of examples that we're getting ready to go through. And I'm going to take you through the easiest way to do these. So the way we're going to do this, it says determine algebraically whether each graph of each equation is symmetric with respect to the x-axis, y-axis, or origin. Okay, so we've got the equation y equals 2x squared over x squared plus 1. For the x-axis, what we're going to do, I'm going to change some red. What we're going to do, our rule here is replace y with negative y. Okay. Okay. And if we wind up with the same function after we replace y with negative y, then it works. Okay, we're reflective over the x-axis. I'm going to go ahead and do the rule for the y-axis and the origin as well. So y-axis rule is replace x with negative x. Okay. The origin rule is replace x with negative x and y with negative y. Alright, so let's work these one by one and you can actually see how it works. Okay, so we've got y equals 2x squared over x squared plus 1. Okay, so treat this y as an f of x. Okay, so we're going to replace y with negative y. Okay, so I guess I just confused you a little bit. But if I replace y with negative y, what I'm going to get here is negative y equals 2x squared over x squared plus 1. Now I need to get y by itself. Okay, so I'm going to divide by negative 1. When I do that, I get y equals, okay, or multiply by negative 1 if you want it to work that way too. Negative 2x squared over x squared plus 1. Now, there's nothing I can do to this equation to get rid of this negative, to cancel it out or simplify it. Therefore, it doesn't work. So this is not the same thing as this. Alright, so because it's not the same thing, it's not reflective with respect to the x-axis. I'm going to go ahead and erase this f of x part because it might be easier actually to teach it this way with just the y's here. But you can treat your y as your f of x. That's always a general case thing. Alright, so let's look at the next one. So if we want to see if it's reflective with respect to the y-axis, we replace x with negative x. And if it gives us the same function, then it works. So that what I get here is y equals 2 times negative x squared over negative x squared plus 1. Now, if I square a negative, it becomes a positive. So I could simplify this to 2x squared over, and if I square this negative x, it becomes a positive x squared. And this is the very same thing as this. Okay? So these are the same. Therefore, since they're the same, it is reflective with respect to the y-axis. So okay. Alright, now the origin. So we're going to start with our original here. Change colors one more time. That one. We're going to replace x with negative x and y with negative y. So what we get is negative y equals 2 times negative x squared over negative x squared plus 1. Now let's simplify this. We already know that we can simplify this to look like this. So I get negative y equals 2x squared over x squared plus 1. If I had to multiply by negative 1 to cancel that negative 1 out, I get y equals negative 2x squared over x squared plus 1. This is not the very same thing as the original function they gave us up top, right? Therefore, it's not reflective with respect to the origin. Okay. Alright, so let's do the next set of examples. And what you really need to remember with this, just so I reiterate it, is what's written in blue. For the x-axis, you're going to replace y with negative y. For the y-axis, replace x with negative x. For the origin, you replace both with negatives. Okay. So here we have y equals x to the third minus 3x. So remember for the x-axis, let's see. For the x-axis here, remember we're going to go and replace y with negative y. Okay, so what I get here, negative y equals x to the third minus 3x. Now if I divide by negative 1 to get rid of that negative 1 out front, I get that y equals negative x to the third plus 3x. That's not the same as this. I can't manipulate it to be the same thing as that. Therefore, it doesn't work. I'm just going to say not reflective over x. Okay, so let's do it for y. Remember for y we replace x with negative x. Okay. If I do that, I get y equals negative x to the third minus 3 times negative x. Okay, so that what I get is y equals, okay, this negative 1 to the third is going to wind up being a negative x to the third. Negative x times negative 3 is positive 3x. So that's not the very same thing as the original either. Therefore, it's not reflective over the y-axis. Okay. Now let's check the origin. Okay, the origin you do both. So you replace x with negative x, replace y with negative y. Let's see how well that's going to work out for us. Okay, so we've got negative y equals negative x to the third minus 3 times negative x. Okay, so if we simplify this, we get negative y equals negative x to the third plus 3x. We divide by negative 1. What it winds up giving us is y equals positive x to the third minus 3x, which is the same thing as the original. Therefore, it is reflective over the origin. Alright, we've got one more example here. What I want you to do is I want you to work this example out on your own. Okay, but what I'm going to go ahead and tell you is that it is reflective over everything. So just so you already have the answer, but I want you to take the time to work it out and make sure you can see that by replacing these things with these things, it winds up being reflective over everything, or all three. Okay, so it's reflective over the x-axis, the y-axis, and the origin, but I want you to be able to show me how. Okay, so take your time, do that. If you have any questions, if you struggle doing that, let me know. I can help you. Send me an email. Other than that, make sure you do your homework, and then move along to 4.2.